Okay.
Oh, yeah. Oh, we're being live streamed.
Yeah. So here also, I think our winter has started.
Yeah.
Yeah. Yeah. So this is my daughter who is running around. Hello.
Hello.
How are you? Hello. Yeah. So today is the final talk for you in this.
Sanju sir, your camera is not, I think, proper. Your visibility is dull.
My visibility dull. I see. Now is it better?
Oh, Papa. ये change करो तो जो blur থাকে background.
Okay, let me log in with a different device.
Hello, namaste. Yes.
Hello.
Yes. So we are enjoying your lectures.
Thank you very much.
With those, yes, it is very nice. So the whole series is going on well, and
That's good. Yeah.
People are seeing on the YouTube, especially later on. Yes.
Very good.
So let us see.
Chair is not able to join the meeting somehow. Khatri sir, can you talk to Soumya?
Soumya, Chair is not able to join. Actually, he was seen. He can join from the calendar, actually Google Calendar. Actually, I joined from Google Calendar only. We'll talk to him. Krishnendu has joined.
Yeah, hello.
Oh, that's better.
Yeah.
Yes.
Yeah, so that was a different device, and yeah.
Chair is saying that she is waiting actually. It is not able to join. I don't know why.
Who?
Anima Nagar ma'am.
Oh, I see. Okay.
So some technical problem.
Okay, so maybe we start, and maybe then whenever she joins, she will join. What do you think? Or maybe we wait for 5 minutes.
Ma'am, let me see.
Yeah. Got it. Hello, Professor Katre, how are you?
Yes, I'm fine.
Yeah.
We are doing well.
Yeah.
So John, in-person classes have started in UK?
Oh, yeah. They're going on.
I see. So how it is so far?
So no, we have everything is almost back to normal.
Oh, I see.
We have some students who
Hello.
be online, and
Yeah.
so they are but
Okay, I will talk
the
to
number
him.
of cases in the university is really, really small.
Okay.
I mean, this time last year, we were having hundreds
all right.
of
I will
cases, and
talk
now
to
we're
some
having
people
like,
also too, but in any case, I will also talk. Yeah.
I see. But in newspaper, it is saying that in Europe, it's very bad. I mean,
so yeah, we've been, I mean, there's a reasonably high case load across the country, but it's mostly 10 to 14-year-olds.
okay.
It's
Okay.
going, at least in our area, it's just going around the schools.
I see.
So the people who are in the university who are getting it tend to be parents
Yeah. So
getting it from their children.
yeah. So for Tintin also, I mean, his school has started, and
Yeah.
he is going in person. Though there is a 50% occupancy, but this is a matter of concern for us, I would say.
Yeah.
Yeah. But let's see how it goes. Yeah.
Yeah.
Our in-person classes will start from next semester.
Okay.
This semester we may start. We will have the exam offline, but
Yes.
things are still online at the moment. Yeah. So, Professor, let me see. So, Devendra, any news about the chair?
He was unable to join. So probably Soumya is working on it.
Okay.
Hmm.
Okay.
Let me also go. Okay. Maybe you
Okay.
can talk to Professor Kulkarni. You can say hi to maybe Professor Kulkarni. Okay.
Hello again. Nice to see you.
Good to see you.
Hello, Professor Kulkarni. So how are you, Professor Kulkarni? Yeah.
Okay, I'm sending you. But
So he is not.
okay. Okay.
I think probably we can start the talk.
Yeah, maybe.
Because the chairperson has some problem, maybe join later whenever possible. So we request Professor John Parker to start the talk. Yes.
Okay. Well, thank you very much indeed. I think this is now my last of these talks. I've very much enjoyed preparing them and giving them. Of course, I would have liked it even more if it had been possible for me to actually visit India and to do this in person, but this is the best substitute that we have in the current climate. So today I'm going to be talking mainly about the Poincare polyhedron theorem or the Poincare polygon theorem, because I shall only talk in 2 dimensions, and about fundamental domains. So here's a basic outline of the talk. I will start up with a bit of an introduction, then we'll talk about polygons and side pairings. Then one of the key ingredients is cycles of vertices, and then I will show some of the issues that arise that mean that this theorem is actually slightly more subtle than you might otherwise think. So let's start the introduction. So I've got a circle of ideas. So let's just start out with a surface, possibly with some cone singularities and possibly with boundary. But let's just suppose that it's orbifold Euler characteristic. So the orbifold there is, if necessary, it's got cone singularities. The Euler characteristic is negative. And so from the uniformization theorem, we know that we can write sigma as a quotient of the hyperbolic plane by a discrete group of isometries acting properly discontinuously. And so this means that there is a fundamental domain D in the hyperbolic plane whose gamma images tessellate the whole of the plane. That means that, so this is the definition of tessellate. We're going to be using this quite a number of times. So this means that the whole of the hyperbolic plane is the union of all of the gamma images of the closure of D. And if we have distinct elements in gamma, then their interiors are disjoint. Now, at some stage, we can make an assumption that either my set is open or it's closed, or maybe it's partially open and closed. Later on, we'll make the assumption that it's closed, or at least relatively closed. So now each point of the boundary of D, so the relative boundary, so I mean the boundary that lies inside the hyperbolic plane. So we'll talk a little bit more about the different notions of boundary in a moment. So each point is going to lie in at least one other copy of D. Maybe this should be, or again, closures here. And then, so this gives us a recipe for gluing the sides of D together again. And if we use that recipe, we come back to the surface that we started with. So we started with a surface, we moved to a group action and a tessellation, and then we got back to the surface again. And we can break into this cycle of ideas at any point. And the Poincare polygon theorem is, it breaks into the cycle by starting with the polygon and a way of gluing sides together, and then that's going to the output is going to be that we have a group which is discrete, its fundamental domain is D, and we have a presentation for the group. So this is where we're going. You'll see all of this in gory detail as we go. But maybe let's think about the example of the torus. So we could start off in any one point in this cycle. So maybe let's start in a slightly different place to where we started before. Suppose that I have a parallelogram, and I glue the opposite sides by Euclidean translations. Obviously, this is not a hyperbolic example; it's a Euclidean example, but it's the easiest one to think of. Well, I could go different ways around this cycle, but maybe one way I could go is, if I go this way, I could then take copies of this parallelogram and I could glue them together by the images of the group. So my gamma here is going to be generated by A and B. And I can glue these together, and I get a whole tessellation of the plane by parallelograms. But if I were to glue these sides together, then I can I obtain the torus in the usual way, or I could take the quotient of the group action, and I would again get the torus, so that I can come backwards and forwards in this direction. And I end up with a presentation for the group, which is the two translations, and then something that goes on around the vertex is going to give me the relation AB, A inverse, B inverse, which tells me that in this case, A and B commute. So we have the generators are to do with these side identifications, and the relation is something to do with the vertices. And this is going to be the general recipe for the Poincare polygon theorem that we're going to see later on. So let's just give a little historical background, and I hopefully will get this right. I'm sure that Professor Kulkarni can tell me if I've made some mistakes here. But the original version of this theorem is due to Poincare. That's why it's named after him. He published a version for the hyperbolic plane in 1882 and hyperbolic three space in 1883 in the early volumes of Acta Mathematica. But then there are versions of this theorem in higher dimensions and in many other geometrical settings. One of my projects at the moment is to try to write down a good version which I could apply in complex hyperbolic setting, but also in other settings. In practice, it's usually quite straightforward to use the theorem. There are things we need to check, but it's usually not too difficult to apply. However, the statement is extremely delicate. And I'm hoping that I will show towards the end of the talk why this is. There's this wonderful paper or interesting paper of Epstein and Petronio from 1994, where they gave a very robust version proof of the Poincare polyhedron theorem. And they also give counterexamples to the statements, if you read them absolutely literally, of every published version, with the exception of one for the plane that was published by Durham. But however, this paper is a very difficult one to read. They're very concerned to be precise. It's very algorithmic, and the statements are they sort of feel a little bit more like it would be easier to read if you're a computer rather than a human being. But it is a very robust version, and it's a good go-to place to understand a lot of the subtleties. Today, my main focus will be on polygons in the hyperbolic plane, and my main examples will be triangle groups, because after all, that is the subject of this special semester. Okay, so let's dive into the beginning of the theorem. So we need to talk about polygons, and again, I'm only thinking about polygons in the hyperbolic plane. And I'm going to have some running assumptions for today that my polygon is connected, convex, and finite-sided. And those are assumptions that I make for simplicity. There are ways that I could relax each of them, but if we do that, then we're going to get involved in all sorts of tricky details, and I want to just concentrate on the main theorem and what's going on with the main theorem. So for today, I will assume that all polygons are connected, that they're convex and they're finite-sided. Now, the polygon might have ideal vertices, or indeed whole arcs on the boundary of the hyperbolic plane. So I'm going to be talking about the boundary of the polyhedron, or the polygon, sorry, and it will have two different notions of boundary. So I just want to be very clear. First of all, the polygon might have an ideal boundary. So that would be the intersection of its closure in the whole of CP1 with the boundary of the hyperbolic plane. And I'm going to call that D infinity the ideal boundary of the polygon. Whereas I'm going to say the boundary, or for emphasis, the non-ideal boundary, is the intersection of the boundary in the usual sense with the hyperbolic plane. So it might be that if D is compact subset of the hyperbolic plane, then the entire boundary is in this partial D. But it might also be that it either has points or even whole arcs on the ideal boundary. So when I just talk about partial D of D, then I'm thinking of just the part of the boundary inside the hyperbolic plane. And for simplicity, I'm just going to have the convention that D is closed as a subset of the hyperbolic plane. That means it's partially closed and partially open because the hyperbolic plane is itself an open set. So I'm going to include this boundary, the DD, but I'm not going to include the ideal boundary. And then the boundary here is going to be a union. Because I said it was finite-sided, it's going to have finitely many sides. And this script S is the collection of those sides, and finitely many vertices, V. And this script V is supposed to be the set of vertices. Now, each side in script S is the arc of a geodesic. That's what I'm part of my assumption that I'm about my polygon. And part of the convexity assumption. And each endpoint of S, that's either going to lie in the ideal boundary, or it's going to be one of the V in the set of vertices. And each vertex in V is going to be a point, and that point is going to be a point inside H2, and it's going to be the endpoint of exactly two sides. That's one of the properties of a polygon. Now, I'm just using this notation is all to do with the polygons in the plane, but let's just talk about how we would adapt this in generality. So sides are codimension 1 facets. In higher codimension, the vertices, the codimension 2 facets would be called ridges. So I could have called these the sides edges, but I'm choosing to call them sides because I would have side pairings, and in higher dimensions I would call these ridges. So later on you'll see that I'm going to use R and rho, and that's because I'm thinking about them being called ridges. So here's our first meaty definition. So a side pairing is a map sigma from the set of sides of my polygon into the isometry group of the hyperbolic plane, satisfying these following 3 conditions. So first, if I have a side S with the associated capital S and the side pairing, then there is another side which I'm putting S upper minus, which is also in the set of sides of my polygon, so that S maps little s onto little s minus, with endpoints going to endpoints. So that would be endpoints inside the hyperbolic plane going to an endpoint inside the hyperbolic plane, and an ideal endpoint going to an ideal endpoint. So if it's a closed interval, then it goes to a closed interval of the same length. If it's a semi-open, semi-ideal interval, it goes to a semi-ideal interval. If it's a total geodesic, it goes to a total geodesic. And moreover, the side pairing associated to this S minus is going to be the inverse of the one associated to S. And in particular, that means that if S equals S minus, there's nothing stopping me at this point in time from pairing a side to itself, then I must have S equals S minus. In other words, S squared is the identity. And that's going to be called a reflection relation. And the obvious example is if my side pairing is a reflection which fixes each point of the geodesic containing the side X. But of course, I could also have something where I had an involution that fixed that geodesic. I'd have a symmetric arc. For example, in the finite arc in the fundamental domain for the modular group. So if I have now I could have think sorts of this is the S, which is being associated with the side X. Okay, don't get sidetracked. Right. So for each side S in the script S with side pairing that S, then the intersection of D with S inverse of D is the side S, and the intersection of the interior of D with its image under S inverse is empty. I'm going to have a picture in a moment to show all these conditions, but just for the moment, let's focus on what the mathematical statement is. And for each point in my side, which is not a vertex, then there's an open neighborhood that is contained in the union of D and S inverse of D. So before I move on, let's just come to the illustration. So I'll slide backwards in a moment. So here is the picture that we have. Here's my polygon D. I have a side little s, and it's going to get paired to a side little s minus. Endpoints go to endpoints. The green endpoint goes to the green endpoint. The red endpoint goes to the red endpoint. Of course, if it was an orientation reversing isometry, then the red and the green would go the opposite way around. But then what I can do is I can I can pull backwards. So there's of course there's the image here of big S of D over there. I can pull that backwards under the inverse map, and so I have little s. That's a big S inverse of D. So that glues along to D along this side S, which is big S inverse of little s minus. And then for every point on the interior of this side, then I can find the little neighborhood UZ that is contained in both of those. That's exactly what I said in these conditions, but I always find it's helpful to have a picture. So with these conditions, we say that big S is the side pairing map associated to the side little s. I think I perhaps even have used that accidentally as I've been coming through. And now we're going to let gamma be the subgroup of the isometry group of the hyperbolic plane generated by the side pairing maps. And of course, we're also automatically going to have the relation that we had up there, that sigma of S minus times sigma x is the identity. And so this set of generators there is closed under inversion. So this is going to be the group that we're considering. So it's important to notice I started with the polygon and the side pairing, and that side pairing gives me the group. All right, so there is the picture of what we just had, and that's my side pairing. So now let's think about vertices. I want to do something very similar with vertices. So let V1 be a vertex in my set of vertices script V. And then by the construction, it's the endpoint of exactly two sides. And remember that you know, V1 V1 is a point in H2. So I'm not talking about ideal vertices, I'm talking about honest to goodness vertices inside. So then V1 is the endpoint of two sides. I'm going to call them S1 and S0 minus. If I chose the other way around, the whole setup is going to work properly. I'm not going to go through the details of that, but I am making a choice, but that choice is not going to matter. So then let's see what happens as we work around with this vertex under the side pairing. So we're going to consider the image of V1 under the side pairing S1 associated to the side S1. So for example, you know, I could think of this, if this vertex V could be my V1, and then this would be S1, and so this would be V2 is S of V1, and so S of S1. Okay, so S1 is sends V1 to another vertex. So automatically it's an endpoint of the side S1 minus. I'm going to call this new vertex V2. And it's the endpoint of exactly two sides, one of which is S1 minus. So I'm going to call the next side S2. So I'm going to, so maybe we'll just, I've got a little picture here. So here is V1. It's the endpoint of S1 and S0 minus. I move across, that's here. I'm going to move across under S1. Little s1 goes to s1 minus, and I get a new vertex v2 and a new side s2. Right, and then I'm going to repeat this process, and I'm going to get v1 is s0 minus intersect s1, v2 is s1 minus intersect s2, all of the way through. Vk is sk minus 1 minus intersect sk. Since this set of vertices is finite, eventually I'm going to get back to the situation where I'm going to have Vm plus 1 is V1, Sm minus is S0 minus, Sm plus 1 is S1. Now, it could be that I come back to have my M plus first vertex with V1, but my sides are the other way around. If that's the case, I go around the cycle once again until I come back where they're all in this order. I'm going to call V1 through to Vm the corresponding vertex cycle. So again, in this picture over here, you can see this. So first of all, I start at V1, I move to V2, then to V3, dot, 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 move to Vm, and back to V1 again. And so let's just examine what happened. So V2 was by definition S1 of V1. V3 was S2 of V2. But of course, V2 was S1 of V1, so it's S2, S1 of V1. All of the way through to Vm is going to be the product of these maps of V1. And then finally, R1, which is the product S1, Sm all the way down to S1. So that means first, of course, first do S1, then do S2, etc., because we always read composition of maps from right to left. That's going to map V1 to itself. And I'm going to call R1 the cycle transformation associated to the vertex V1. Now, let's just do a little aside here. If I had gone the other way round this cycle by choosing S1 and S0 the opposite way round, then what I would have done was I would have done exactly the same thing, and I would have got R1 inverse coming up. So really, R1 is only defined up to a plus or minus 1. Okay. So that's a vertex cycle. And what I want to do with this is I want to see how all of these images of D, they all fit together around V1. So I'm going to do this formally on the next slide, and let's just think about how this works by looking at this picture. Okay, so what we already knew that S1 inverse of D glues together along S1. And so then I can also glue the next one along on the next side. So that's a bad color, maybe use V. So that's going to be S1 inverse, S2 inverse of D is going to glue along that side. And what happens is I come all of the way around, and eventually I get on the top right hand side, I get M copies of D all glued together around the vertex V, and then this map R1, it's going to map the very last side back to the first side. So what I call this picture on the top right hand here, I'm just going to say this is a wedge of copies of fundamental domains, because it looks like a wedge with endpoint V1. So then I want to formalize this notion of how these things glue together. So I've obtained M copies of D. glued in a wedge at V1. So as I just said on the previous slide, but let's say it again, D is glued along S1, which is big S1 inverse of S1 minus to S1 inverse of D. And then S1 inverse of D is glued along S1 inverse of S2, which is S1 inverse, S2 inverse, a little S2 minus, to the next one along. And so that was the picture we had. The first one, we had D, we had S1 inverse of D, we had S1 inverse, S2 inverse of D, and so on and so forth until we get down to the mth copy, which is S1 inverse dot 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 Sn minus 1 inverse of D. And then the free sides are the very first, the S0 minus in D, in the very first one, and S1 inverse all the way through. In there, it's this side, this last side, which is R1 inverse of S0 minus. So R1 fixes this vertex V, and it pairs the sides R1 inverse S0 minus and S0 minus. Just like the original side pairing map, but this is like a generalization on this wedge of sides. And what I want to do is I want to have a tessellation in a small neighborhood of V1. And so what needs to happen, so I've got this wedge now up on the top right-hand side, and I can repeat this, and I'm going to end up with a whole lot of images of this wedge, and I want them to beautifully fit together. And so far they fit together without overlap, but I need them to fit together all of the way so that at the very end they all match up. And so what that means is that I need to have a natural number L, so the R1 to the L is the identity, and this is going to be called a cycle relation. This is an important thing for later. And I'm going to define the cycle at V1 to be all of these maps that I've generated as I went through. So it's just convenient to not have the inverses. So I started out with S1, then I had S2, S1, and then eventually I came all the way through to Sm minus 1, all the way through to S1. And then I had R1, which was Sm, all the way through to S1. And I keep on going. And eventually I get this cycle. Now my convention here is that if J is equal to 0, then I have none of these maps there. None of those maps appear. And of course, if K is equal to 0, then I don't get any R1, Ri. So that should be an R1, not an R. Okay, so that's my cycle. So this takes a little bit of going through. In practice, it's going to be quite easy, but the theory is. So now I'm going to use this, and I'm going to mimic the side pairing conditions to give me my cycle condition. Okay, so let's do the setup again. Okay, that should be a 1. So I've got my set vertices. The vertices, I've got a map. Rho is the map that's sending the vertex V to its cycle transformation, rho of V, which was and rho of V1, which is R1, which as constructed above before with S1. And then let C be the cycle at V1, which is just what we had a moment ago. So actually what happens is if I were to write out the word R1 to the L, then this is all of the subwords starting from the right-hand end that I could possibly go, or M times L subwords of that. So then the cycle condition at this vertex V1 is first that this vertex should be the only point in the intersection of all of the images of D under the cycle. It should be in there. It is in there by construction, but we want nothing else. That's quite easy in this situation, but in higher dimensions, when you've got an entire ridge, you need to be a little bit more careful there. If I have two distinct elements of my cycle, then the inverse images of the interiors of D are empty. So they have empty intersection. So the interiors of all of these cycles have empty intersection, and there is an open neighborhood of this vertex, which is contained in the union of all of the things around the cycle. This is very much like what we had before for the sides. So remember that for the sides, we would just have that S was D intersect S inverse of D. We would have that D naught intersect S inverse of D naught, B naught. It's empty, and that if I had a point and I have this sort of point Z in S not equal to a vertex, and I would have this U. So it just mimics the same conditions as we had before. So in the situation we've just seen, where we had a wedge of copies, wedge at V1 of copies of D, the sides of this wedge are paired by R1, and the cycle condition is equivalent to R1 rotating the tangent space at V1 by 2 pi over L. And quite often, this cycle condition is given in terms of angles, but I wanted to do it specifically not in terms of angles, because we may be in a setting where we don't have well-defined angles, and in higher dimensions, that's also a problem. So this is a way of stating the condition without resorting to angles. Although, of course, I could do that in this case. And I want to notice that if the cycle condition at V1, it's easy to see it's satisfied at all of the other vertices in the same cycle. And what you do is you just cyclically permute the word R1 and all the way through. Okay. So here is a picture of what local tessellation at a vertex looks like. So we had this wedge of copies of D, and so there's a blue wedge is my original wedge. This is my wedge. And then its image under R1 inverse is another wedge, which is a green wedge. So this one, R1 inverse of the original wedge. Then I come round and there's the start of a black wedge all the way through down to the yellow wedge at the far end. And those should all beautifully fit together around the vertex V1. So the interiors are disjoint. Each one intersects the next one along a side, and their common intersection, the only point is the vertex, and their union covers a nice little neighborhood of red, a nice little neighborhood UV1. So let's talk about the example of a triangle group. And I'm going to think about the orientation preserving triangle group. So we could have talked about the reflection triangle group, but this one just shows a tiny bit more interesting phenomenon. Okay, so let's suppose I've got a triangle T with internal angles alpha, beta, gamma, and I'm going to make a quadrilateral made of its image under reflection in one of the sides. And so here is my quadrilateral. So my original triangle is the one that's on the right-hand side there, and the one at the triangle on the left is the image of the reflection in the sides joining the vertices with angle alpha and beta. So then I have side pairings, which are going to be that I have this green side SA in the original triangle, and it's going to be paired to SA upper minus by a map A in and similarly I have SB is paired to SB minus by a map B. So what is the cycle transformation at VA? Well, VA is the intersection of SA and SA minus, so I only have my wedge has only one copy of D in it. And so what I need to have then is that this map A to the A has to be the identity, and that means that this angle to alpha has to be 2 pi over A. Similarly, the cycle transformation at B, again, my cycle only has one copy of D in it, and so that means that I want B to the B, and that should have been 2 beta. It should be equal to 2 pi over B. Now something slightly more interesting happens at VC. It gets mapped across to VC prime under A, and then it gets mapped back to VC under B. So here at the bottom of the page is a picture of the cycle transformation, so the wedge associated to that pair. And so now I need my cycle condition says that I must have C, so that BA to the power C is the identity, and then 2 gamma, because I had a gamma from each one of them, is equal to 2 pi over C. So that's shown that if I have the cycle conditions, so cycle conditions implies that alpha is pi over A, beta is pi over B, gamma is pi over C, where A, B, C are. So this, we know that that's what we should be getting, but this is how that comes, that angle condition comes out of this cycle conditions. Okay, so let's just recap where we're up to. So we've got a polyhedron D with sides S and vertices script S and its vertices script V. We have a side pairing map which associates to each side an element of the isometry group of H2. And they also imply that copies of D tessellate open neighborhoods of each point of the side apart from the vertices. And now we also have cycle transformations at each vertex. That's rho going from V again to the isometry group. And the cycle conditions imply that copies of D tessellate open neighborhoods of each vertex. So since all points in the boundary were contained in either a side or a vertex, we now can tessellate at every point. Of course, we have local tessellation on the interior of D. Simply, we put a little open set that's contained in the interior, and we have one copy of D in there. So we have local tessellation at all points of D. Now, let me just pause for a moment. In higher dimensions, one of the most amazing things about the Poincare theorem is that I do not need any extra conditions. I have to use some sort of induction argument over dimension, but I only have side pairings and cycle transformations on the codimension 1 and codimension 2 facets of my polyhedron, and then from that I can generate local tessellation around all higher codimension facets. So, but as we're only dealing with polygons today, we don't need to do that. So what we have now is we have local tessellation around D. So all points of D, I can find a little open neighborhood where I have which I can cover with copies of D whose interiors are disjoint. But what I need now is I need a local to global phenomenon. I need to be able to tessellate the whole of the hyperbolic plane. It's particularly easy in the case where D is compact. So let's just think about that case for a moment. So what happens is I get an open cover of D just coming out of the side pairing conditions and the cycle conditions. If D is compact, by definition of compactness, every open cover has a finite subcover. And so what I can do is I can assume that that finite subcover, each one of those open sets contains an epsilon ball for some fixed epsilon. So I have a given epsilon positive, so the epsilon neighborhood of the whole polyhedron, the polygon, is tessellated. So let's just look and see what that does for us. So here I have my blue polygon. I have my fixed epsilon, and so the blue polygon, and then that's contained in this U epsilon, this epsilon neighborhood, and that we have local tessellation. So local tessellation implies that there's a green collection of copies of D that will cover all of this epsilon neighborhood and will tessellate it. So they all have disjoint interiors. Now, each one of those images of D that has an epsilon neighborhood that is covered by copies of D. And so this green collection is contained in the epsilon neighborhood of the union, is the union of the epsilon neighborhoods. And so we can repeat this. So that means that if I take some point out here, Z, I can join that by a path of finite length to my polygon D. And then all I have to do is cover that path by epsilon balls, and the center of each epsilon ball is contained in a copy of D, and then that epsilon neighborhood is contained in more D's, and so I can move to the boundary of that epsilon neighborhood, and so I can just sort of slowly work my way along that path using epsilon neighborhoods to show that Z is contained in a set which is tessellated by D. Z was arbitrary, and so eventually I get local tessellation. I get tessellation of the whole of the hyperbolic plane. Now, I have to be slightly careful that these things don't come back and overlap in a far distance, and for that I actually need a covering space argument, and so I'm not going to talk about that. Again, that's one of the subtle points which in the Epstein-Petronio paper, if I'd have just simply said this was the argument, then that wouldn't have worked. So I have to work a little harder. But it actually does work. It's basically because the set I'm getting as I go is simply connected. Right, completeness in the non-compact case. So that if the polygon is not compact, that means that there's at least one point of the boundary, the ideal boundary of hyperbolic plane in its closure. So that means, well, the trivial case, the polygon could be the entire hyperbolic plane. Tessellation is simple, there's no group involved, it's trivial. So let's just say we've got a side with at least one end at a point of the ideal boundary. So I'm going to use Greek letters to denote the ideal boundary so that we don't get confused. So again, so that's this psi here. Maybe I want to have a different color. And so again, let S be the side pairing map associated to the side S. S minus be the image under big S of little s, and psi minus be the image of psi under big S. And we know from the side pairing conditions for any z on S, I have a neighborhood, an open neighborhood contained in D union S minus. And let's just suppose that, that this contains a ball of radius epsilon of z. There's a simple case which we can rule out. It's actually going to be subsumed in what I say later, but let's just think about what's going on. Let's do it step by step. So let's first of all suppose that psi and psi prime are not the endpoints of any other edges of D. And so that means that I can choose this epsilon of z as my little point. So remember I had this little neighborhood here, which has got an epsilon ball. I can, as this point sort of tends down this side S towards the endpoint psi, then because there are no other sides asymptotic to it, then the epsilon neighborhood of the side is this thing that looks like the end of a banana. So maybe I could just draw this, that if the side was a vertical line, then this would just be a wedge coming in. And then it's the image of that picture under other transformations. And so this would mean that I could always make sure that as I tend down this side, my epsilon tends to a positive limit. And so what I can do is I can then assume that that this epsilon, if this is the only ideal endpoint, this is the only thing that happens, then I can adapt the previous argument to show that away from some sort of neighborhood of some open neighborhood of this endpoint, actually what I could choose is I could choose a horosphere, a horoball. Away from that, then everything's compact, and I use the same argument as I had before, and I adapt the previous argument. So the key case that we need to consider is where we have a psi, which is the endpoint of at least, well, of exactly two sides of D. So let's just see what can go wrong in that case. So let's just think of a very simple case where D is this strip here in the upper half plane model between 1 and 2. That's D there. And it's the left-hand side is where the real part of Z is 1, and the right-hand side is where the real part of Z is 2s minus. And let's just suppose, obviously I could pair that using the translation Z goes to Z plus 1. But let's suppose I choose to do it in a slightly strange way and to choose this map S, which is Z goes to 2Z. That's perfectly good. It maps this geodesic, the geodesic little s to the geodesic little s minus. It maps infinity to infinity, and it maps the endpoint 1 to the endpoint 2. Now let's see what happens if I take images under integer powers. Well, I get a strip between 2 and 4 is the image under S, between 4 and 8 is the image under S squared. But now if I go to the left, the image under S minus is a strip between half and 1, and then the next is a strip between a quarter and a half, and so forth. What happens is everything piles up on this, excuse me, on this vertical line, which is the imaginary axis. And I never ever cover points in the left half plane. So I don't get global tessellation. So this is something that could go wrong, and I need to be a little bit more careful. So the answer to this is that we have consistent horoballs. So let me try to define what this is. So just to remind you that a horoball is just move this down slightly. A horoball, this would be the upper half plane model. The horoballs centered at infinity are points that are above a certain positive height. And then at a finite point, there would be open disks that are tangent to the boundary at a single point. The red disk is tangent to the boundary of a hyperbolic plane at the point infinity. So that's more or less what I've said here. Okay, so that's what the horoball is. So that suppose we've got a vertex, an ideal vertex psi1, that's the endpoints of S0 minus and S1. So that's just like we had before. So maybe here, let's again call this. So we've got my ideal vertex psi1. I've got our edges S0 minus S1. Okay, so we can mimic the whole construction of a vertex cycle. It may be that this vertex just gets mapped to itself, but it may be that it goes around a finite. And again, because I'm assuming finite sidedness, that we're going to get this cycle of ideal vertices. Each one of which is and so psi j is the endpoint of two sides, sj minus. And eventually we come back to the point where we have psi. This is just like we had in the previous in the vertex cycle construction. And suppose then that that big Sj is the side pairing map, which is a little Sj. So a system of consistent horoballs at this vertex cycle are horoballs based at psi1 all the way through to psi m, so that each one is the image of the next under the side pairing map, and eventually the cycle all comes back, and I come back to the same one. So let's come back to my previous example here. Then what I would have got is I would have got a side. So perhaps this would be S1, and then it would. Sorry, I wanted U1. I don't know why. No, S. So this would be U1, this horoball here. But then when I come back, then S1, S of U, S1 of U1. And so these two things are not equal to each other. And so this is what fails in this case. Okay, and so then the final hypothesis of the Poincare polygon theorem is that there exists a system of consistent horoballs for each cycle of ideal vertices. So let's finally state the theorem. We've got a polygon D, side pairing sigma, satisfying the pairing conditions. At each vertex, there's a cycle rho, satisfying the cycle conditions. And there's a system of consistent horoballs at each ideal vertex. In this case where we had there were no pairs of sides, then that would just be a redundant condition. But a system of there would only be one horoball, two horoballs. Okay, so if we have all of these conditions, then the group gamma. Remember that gamma was the group generated by the side pairing maps. That is, we conclude that is discrete. The polygon that we first thought of is a fundamental polygon for gamma. So that means its images under gamma cover the whole of the hyperbolic plane and their pairwise disjoint interiors. That means that they tessellate. And with this generating set, the reflection relations coming from sides paired to themselves. I guess I should also have added in here the condition that the sigma of S minus is sigma of S inverse. Those relations, it's essentially coming from the cycle, the reflection relations, similar set. And then so with the reflection relations and the cycle relations, they're a complete set of relations to give a presentation of the group. So let's finally come back to this example that we talked about before. So we've got this domain D, which is a quadrilateral made up of two triangles. We have the cycle relations. And so here, my group is going to be A, B, such that A to the A is B to the B is B, A, C is the identity. And so that gives me the usual presentation for the triangle group. And that's it. Thank you.
Thanks, Professor Patel.
Oh. Yeah, so John, I have a question here.
Yeah.
Yeah. So Poincare's polyhedron theorem, that essentially you start with a polygon.
Yep.
And then you try to obtain a discrete group.
Yep.
Whose fundamental domain is the polygon.
Correct.
Now, what about the converse question? I mean, is there any general setup, like you start with a discrete group, then can you get?
Yes, indeed. So, so perhaps a method that will always work is the Dirichlet construction. And so what you do there, maybe what I'll do is I'll close this up and then I will just get a blank piece of paper so that I can there should be a better way of doing it, but never mind. Okay, so this is the Dirichlet construction. So you're saying that I have a group gamma acting, or maybe let's say X, which we can think of as the hyperbolic plane, and it's a group of isometries. And so here's a picture. What I want to do is I choose a point Z0, so we're going to have Z0 H. Now I look at all of its images under elements of gamma. And so let's let Z1 be G1, sorry, Zi, Gi is Z0, where Gi is in gamma. And so it runs through all possible site elements. So here's Z0, and somewhere over here, let's just say is Z1. And then what I do is I look at all the points that are closer to Z0 than to Z1. So I look at all Z in H2 such that the distance from Z to Z0 is less than, perhaps less than or equal to the distance from Z to Zi. And maybe just to emphasize that. Gi Z naught. Right, and so maybe here's another one. Z2. And now I take so that one gives me a half plane. Maybe we'll call that HI. HI for half plane, and then we take the intersection over all I in all GI in gamma of HI. So maybe I can, that would just picture that was just that I'm just taking that intersection. Now that's going to give me a fundamental domain, provided that Z0 does not have any, is not fixed by any element of the group. So, eventually you could come. Now that's great, but the problem is that so this is the Dirichlet domain. The problem is that for the hyperbolic plane, it's not so bad, but in general, this can have infinitely many sides, and you don't know which elements of the group are going to contribute to those sides, and so it's a particularly delicate thing, and so you have to basically use an algorithm that you start out and eventually you close up, but it's something that is actually quite hard to implement. So yeah, that answers your question. But so there are often better ways of finding a fundamental domain given a group. That was a very long answer to a short question. So I apologize.
Hello, Professor Animanal.
Yeah, hello.
How did you manage to join?
I finally uninstalled Zoom and then installed it again.
Oh my word, that's a difference.
But that took a long time, and actually I thought it shouldn't be so difficult because you usually attend Zoom meetings, but I don't know why it was giving a problem today.
Okay, so thank you.
I have a question actually.
Okay.
Yeah. So the question is that when you talk about tessellations, right? Your fundamental polygon that you consider should have like the edges or the angles at the vertices, right? Should be rational multiples of pi. So what happens, like how do we deal with the case if you have an irrational multiple of pi as an angle there? So how do we deal with that case? Yeah.
So the only, let me come back into my my talk again.
Yeah.
So let's come back to maybe this picture here. This is where I needed to have, so there's this, it's not, okay, so what did I need to do? I needed to have the sum of the angles in the wedge. So I needed to have the sum of the angles in the wedge is 2 pi over L. So that it could well be that if I looked at this wedge, so this total angle is 2 pi over L.
Yeah.
But maybe each one of these could be anything, these angles.
Okay.
Yeah, that's okay. The one thing. And the second thing is, if L is equal to 1,
yeah,
then this whole thing closes up with just one copy of the wedge, which is usually often is the case if you don't have any. So for example, if I try to do this with a surface group, then everything would just close up with just one copy. and then there's no need for anything to be rational multiple of pi.
Okay. Because I was looking this from the point of view of billiards, because if you are looking for a billiards, you're looking into the dynamics of billiards, you generally need a tessellation because you want to like construct the billiard orbit, right, tending to infinity. So if you have irrational, like if your polygon, your fundamental polygon contains some kind of irrationality there, then that could lead to some kind of problem. I mean, okay, this method, I'll try to think over it, how one can deal with this, but.
So the simplest case when you're doing billiards, so what you're wanting to do with billiards is you're wanting to take your polygon and then unfold it. Into
Exactly.
into lots of copies.
Yes.
And so that's going to, I mean, if you start to fold around a vertex, you don't necessarily need to come back to where you started from, but you can, it can perhaps go to a covering surface.
Okay.
So maybe, and so you're not, if you have a tessellation, it's going to make your life easier in a billiard.
Yeah. Yes, exactly.
But you do not need a tessellation. You could just have a multiple cover by unfolding all of the way around.
Okay.
And so that would often be the case.
Okay. Worth trying. Maybe I'll try it out. Thanks a lot.
Okay, thank you. And if you have any questions, do feel free to email me and I can try.
Yeah, sure. Definitely. Thanks a lot.
Okay, you're welcome.
Hello.
Hello?
Yeah, I have a question. If actually for Poincare polygon, is that is there any theorem exist for non-orientable and orientable cases?
So I did not say anything about the orientable or non-orientable in this case.
Yeah,
I could have just used all I said was in the isometry group. So for example, let me come back into here. Let me see if I can. If I were to take a triangle here with angles maybe pi over A, pi over B, pi over C, then I could think of maybe S1, S2, and S3. So I could have taken this the case where S1 is paired to itself by reflection, and similarly for S2 and S3. Then when I started with my vertex cycle, so maybe let's just say let's call that one V3. So then I would have V3 with S1, S2. Then I can do my first reflection and they come back the other way round, S2, S1. And then I come back again and I come back to V3, S1, S2. So perhaps this would be the reflection, maybe first of all do big S1. Actually, okay, so this should be S1 inverse of D. So that's perhaps not. So yeah. So I'm sort of reflecting